Good afternoon, everyone, and welcome to this LinkedIn live interview that is brought to you by the Human Brain Project. I'm Lisa Otten, and I'm the project manager in the Human Brain Project at the Aix-Marseille University in France. Today, I have the privilege of interviewing a PI, a principal investigator of the Human Brain Project, who is called Svenja Caspers. She's the director of the Institute of Anatomy 1 at Heinrich-Heine-University, and she's also group leader of the connectivity group at the Institute of Neuroscience and Medicine of the Research Centre Jülich in Germany. And today, our discussion will focus on how Svenja's team has used the Human Brain Project's digital research infrastructure, that is called EBRAINS, to address one of the oldest enigmas in neuroscience, the dichotomy of brain structure and function. So now I would like to welcome her to join me on screen. Svenja, are you here? Yes.
Hello, Lisa.
Hi, so good to see you. How
Great
are
to see you? Fine, thank you.
Cool.
Hope the same on your side.
Yeah. Are you ready? Shall we start straight away?
Of course.
Okay.
Looking forward.
Yes, me too. So I'll start with my first question. Already looking at the title of this interview, which is Degeneracy, is big data big enough? I come up with the first question. What, Svenja, please explain it to me. What is degeneracy?
Yeah, when we talk about degeneracy in a system like the brain, we talk about a specific feature of the system. Our brain is a very complex organ. It has a lot of different components, and all of them work together to fulfill our everyday functions. That's basically the idea of how our brain works. And the specific thing of the brain here is that different types of structures in the brain subserve basically the same kind of function. For example, if you look at our motor output, like moving our hands and our feet and walking through our environment, this is done and supported by a lot of brain structures, all of them ending up in something like a motor output. But now comes the important thing. We do not have like 10 structures and 10 components doing exactly the same to serve this motor output, but each single component has a different sub-function. And each is very important to have the whole system working. But now, if you have something like a lesion, a destruction of tissue, and a specific component is lost in the brain, then you do see that each component with its specific function would be able to somehow compensate for the loss of this one component. So in the end, you have, again, something like a general motor output, but with a different combination of all these components subserving it, minus the one that was lost due to destruction and some tissue damage. For example, in a stroke or similar examples. And it's important to somehow differentiate that from this basic idea of having a lot of components subserving exactly the same function, which would be redundancy. For example, a simple computer storage would be a redundant system because you do not want to lose any data. And if anything is destroyed there, you can just fill in the memory space on a different part of the storage system. But it's basically the exact same function, storing data. But in the brain, each single component has different subfunctions. And that's the difference between redundancy and degeneracy, and very important and very interesting actually to study in the brain, because if we would have understood that completely, then maybe we would have understood the complexity of the brain organization overall.
Okay, so it's a very essential question. Well, maybe you could go more into what your personal research focus is. I know we are talking about, especially in Work Package 1 that we are part of, there is something like a showcase. So you are part of Showcase 1. And so you're focusing on something very specific there. Can you maybe go a little bit into detail here?
So in general, our showcases have the idea to demonstrate how our digital infrastructure, EBRAINS, can be used for different kinds of questions. And our specific showcase is focusing on the question how we can use the systems level perspective of the brain, so the brain as the whole system, not necessarily on the molecular or cellular level, but on the whole organ level, and try to model aspects of this organ given a given structure, given some basic components that we know how the system works, and try to model some functional effects. That sounds a bit strange at first sight, because we are probably not proposing to just say we can model the human brain. That's too easy. But we are able to model specific aspects of it and general functionalities. That's the idea of the showcase. And for our specific showcase and my research focus, we started off with trying to understand aspects of the normal variability in the human brain. We are all completely different individuals, and so are our brains. They are basically structured in a similar way, but each of us has his or her individual brain. And to better understand these types of variability, modeling might be a way to help us there. And my specific question is how aging works in the brain. Like our normal aging process as we get older, what happens in the brain, because particularly at this point in time, we do see a lot of variability. And that's the question of this showcase. Can we model things like aging effects? Just to put it in one question.
Okay, that sounds really interesting. I think I will have more questions to that later on, the aging. That's quite interesting. So basically the keywords here are variability, but also individuality. So these are the two major points that I just picked out that you are addressing, right?
Yeah.
Okay. So I imagine that, so when you're talking about the brain, you're talking about certain aspects of the brain, not necessarily the brain at one, as a whole entity. How, like, what are you basing yourself on? So you're working with certain data sets, I imagine. What kind of data sets are you using?
So to feed the models that are built somewhere else, we do have a lot of data from the general population, from people in different countries, particularly in our case, for example, for a larger group of subjects, over 1,000 subjects of the western part of Germany. And we have been measuring them using magnetic resonance imaging. So basically creating brain images in different types of measurements, focusing more on the structural side, focusing more on the functional aspects of the brain. And based on these data, we are able to describe, first of all, and then also disentangle and characterize the specific differences in each individual, together with all of the influencing factors that might surround us, starting with our genetics, which is not surround, but inside of us, but all the surroundings like our environment, our lifestyle, our everyday business, and things like that. And all of us might influence us. And together with these brain images, we can try to better understand that, correlate these data, and finally put those into modeling approaches.
Okay. So here you're talking about whole brain modeling approaches. Can you just explain a little bit, how can we understand this? What does this mean? Like, before you were talking about, we're only using like certain sub areas. Now we're talking about whole brain modeling. Like, this sounds quite intriguing.
The idea here is that we take the system brain as a whole. That's the part whole brain. But we do not expect to have modeled every single thing which happens in this whole organ. But we take the perspective of having the whole organ as our focus. Instead of, for example, there are also models available which just look at specific neuronal circuits of like 5 or 10 or hundreds of neurons, not at the whole organ brain. And that's our major focus in this specific showcase.
Okay. I'm starting to follow a little bit. Like, so this is again the question where the complexity and the degeneracy comes from, right? Like, okay. All right. So tell me, Svenja, you are part of the Human Brain Project for how many years?
Yeah, now it's becoming almost 3 years for this last part. We are approaching our final phase of the Human Brain Project. And I started off in the second last phase, so it's overall it's about 6 years almost.
Okay, and well, when you look back, what do you think? Like, how could you benefit from the Human Brain Project? Like, how was it possible for you to do this type of research that you really did here in the context of the Human Brain Project that you would not have been able to do otherwise?
Yeah, I think there are different aspects to it. First of all, it's the infrastructure. On the one hand, that you have been mentioning at the very beginning, we have this digital infrastructure called EBRAINS. And this EBRAINS infrastructure is some kind of, would not call it a model necessarily, but some kind of really an infrastructure putting everything that we at the very moment know about the brain, different aspects of it, into one single container, so to say. And this container has information about the molecular architecture of the brain, about cellular aspects of the brain, about the connectivity, so the communication between different parts of the brain, and about the different parts of the brain itself, the areas of the brain. And if we put all of that together, it can help us to integrate across these different levels of organization. If we know what the different neuronal circuits are doing, like if only 5 or 10 or hundreds of neurons talk to each other, and then integrate that into the next level where we have the brain areas and know how one brain area with a lot of thousands to millions of neurons is working, and then again go to the next level and put all the different brain areas together and connect them and see how they then interact. We do have a hierarchical model or approach that would hardly be possible without such an endeavor as the Human Brain Project, because we have all the different groups all over Europe who are contributing to this endeavor and who are contributing their specific expertise and data on the different levels, which is typically that not every neuroscientist is working on every level, but it's very specialized. And now we have everything in one container and can now ask questions that we would not have been able to ask before that. For example, refining this model that I was just describing before. There are different brain areas, they are somehow connected. That would be the model that I would be focusing on, because I look at the whole brain as the system from this very top level of organization. But if we go all the way further down, we can now better describe how this area is composed of different types of neurons, how they work, how they are interconnected between each other, what types of neurotransmitter receptors are, for example, relevant, and so on and so forth. And with that, we hope to better refine our models so that in the end, the models would be better able to predict things that we see in our empirical studies. So that's one major aspect, I think. And the other one is a very simple one, I think. It was just nice and is still nice to have been connected via the Human Brain Project to so many different groups all over Europe. And in our special case here for our showcase and for the work that I'm doing, that we now work together with the group of Victor Gilza in Marseille University, and to link the empirical with the modeling world more closely.
Okay, so I can see really this kind of multi-scale approach that you are, that you're really working with, and teamwork like all around Europe. Okay, that's really great. And so basically, I can see you are saying that the EBRAINS infrastructure does facilitate this research enormously. What do you expect? How can in the future, how will you be able to still benefit from it, and how would other people that are maybe not necessarily connected yet be able to benefit from this and from all the data that you were describing?
So for us personally, I think it would be definitely interesting to further develop our modeling approaches. For, as I said in the beginning, we have been starting with aging effects, just looking at the factor age itself. So if a subject is older than another one, what does happen in the brain? What would be interesting for us is to include more information about these effects first of all. So integrate all the different levels that we have not been integrating so far because we just started off with that. And integrating different types of factors and trying to simulate or model effects of the lifestyle, for example, or of our environment. That would be interesting to see if we are able to do so. It's still a way to go. But that could be something where the EBRAINS infrastructure can help us to have, at best possible, all the data available that are around there, and to create the best available model at that point in time to just make some progress in understanding this, particularly this variability aspect of the brain. That would be my major interest, so to say. Like, why is one person with 90 years old already or still quite fit and healthy and engaged in everything, and another person like with 70 years old might be already quite have quite some problems in everyday life. That is something that would be interesting, and that could be also something for people more at the very moment, potentially more outside of the HPP, for example, to create, in the end, that's still a long way to go, but in the end, maybe create more individualized therapeutic approaches. If we better understand how an individual brain looks like and what exactly in this brain might be going on, then this could be at least a chance to individualize therapeutic approaches and better understand things like neurodegenerative diseases or things like that. And on the other hand, it could also be that people use our showcase setting where we just demonstrate how to use this infrastructure for understanding brain structure function relationships and variability aspects to pose completely different questions and set up their own model and try to integrate all of these data that I was just describing across the different levels of organization of the brain, and hopefully have new insights that they did not have before.
Okay, so from what I understand what you are saying, it can be, on the one hand, be used by medical doctors, for example, because you were using the word therapeutic.
Maybe.
And at the same time, wait, yeah?
That would be interesting, actually.
Okay.
If we could reach such a step, which is definitely a way to go. But that would be something where it could go to.
Okay, that's interesting. And then at the same time, also for researchers to kind of take up your research ideas and develop them further and create new collaborations. And is this how, do I understand this correctly?
Yeah, of course, we are always happy to further collaborate, but also just to use it really as a demonstrator how EBRAINS can be used, and whoever wants to use it can use it on his or her own without needing us for that, but just to use the idea that is behind our approach and to use it for completely different questions. I mean, there are totally different ways of looking at the brain and different modeling approaches, for example, and that could be interesting if people just think, oh, now I have a new idea and a new approach that I can try on my own data, for example. Okay,
so basically everybody who is interested in this could kind of connect and benefit from this.
That's the idea and the hope of this very large infrastructure and all the background work.
Okay, great. And apart from that, what are the kind of further developments? Like, you were talking about now how we see EBRAINS now, but like in the future, is there a possibility also for patients to benefit from it, or what is foreseen for like basically the outcomes of the Human Brain Project and EBRAINS?
Well, going again in this direction of the therapeutic approaches that might come out of it once in the future, I think patients could benefit from it, and that might be something that next week in our next seminar, my colleague will talk about, when we start to model specific diseases, for example, a brain tumor or epilepsy. Then we could really go into this whole container system of EBRAINS, put everything together that we know in there, and try to better understand what exactly is happening in this particular disease case. What does the tumor destroy? Where exactly is it located? What goes in and out of there? And what types of different neurons, transmitter receptors, or so on might be, or systems of that might be affected? And that can be something that on a basic level can be done already now, probably, but not with this complexity of data and by using all of the available information. And with that, then maybe the patient himself or herself could benefit from this outcome because the doctor knows better how to set up the correct therapy and have a maybe optimized strategy of how to do the surgery or how to set up the medications or whatsoever.
Okay, so it can actually be used as a tool in itself.
Yeah, something like a tool. Mm-hmm.
Okay.
Yeah.
And let's say, so I told you I'm very curious about this aging part now.
Mm-hmm.
Let's say I go into a brain scanner. We have nice brain scanners here in Marseille. I ask for all the data that I can get about my brain. I send them to you. You have a look at them. Will you be able to tell me if I'm aging well, if I will be aging well in the future, and what I should take care of, and can I use it as a preventative tool? And what will you be able to tell about myself directly?
A very nice question, and probably one of the most interesting questions that we all can think of. As I said, for the question of where EBRAINS might go to and who might benefit from it, it is still a long way to go to do things like more individualized options when you model a brain or when understanding the individual brain. But I hope at least that we could come to a point where we better understand what exactly goes on in your brain when you give me your brain scan, as compared to the situation that we had just like a few years ago, where all of this started more intensely, so to say, where the focus was major on group level analyses. So we have a group of subjects and a different group of subjects and compare the effects between the two groups. And then it's not necessarily the case that for you in group 1, this might be exactly true. It could be somewhere around it. It could be in general true, but there could be these little differences that might be particularly relevant for your brain and for your specific aging effects. But now comes the problem. We are not there yet to have identified these individually relevant factors that could help me to tell you, based on your brain scan, what you could do, what you should do, if this could be a preventive strategy. Just take a brain scan and let it be analyzed and then know what to do in the next 20 to 30 years. That would be easy, but I think this is something for the very, very far future, if at all. Because we definitely have to better understand a lot about the brain to really say things like, this is your aging way in the brain.
Okay. I mean, you are already talking about using different variables to kind of get closer to this, right? Like taking into account environmental variables, and I guess we would get closer to being able to predict something about the individual. I remember that before that you also mentioned something about genetics. How would that be? Like, how can you use a variable that is just the genetics? Like, do you talk about the human genome, or I don't know, how can I understand this?
Yeah, like in the environment or our lifestyle, which is not the lifestyle or the environment, we do have a lot of different parts that contribute to the lifestyle, to the environment. Like, could be the noise in our environment, could be the air pollution, could be anything, the greenness, I don't know, whatever is surrounding us. And the lifestyle could be things like our nutrition, our alcohol consumption, our smoking behavior, doing sports or not, being socially integrated or not. So a lot of different factors, but all under the umbrella of lifestyle. And the same is true for the genetics, basically. We talk about the genetics and the genome, but this is composed of millions of different genes and components of the genes. And some of them are quite relevant for specific diseases. And this is where the idea comes from, that of course our genetic endowment somehow makes us humans and is responsible for all the cell functions and for everything that organs in our body do. But some are more important for our brain functions. And this is where we would like to better understand which factors these are, and specifically also which contribute to diseases of the brain. For example, neurodegenerative diseases like Alzheimer's disease, Parkinson's disease, or some of the psychiatric diseases for which we also know that there are genetic influences. So it's again a number of different factors, together with all the number of different lifestyle factors and the number of different environmental factors, and you end up with thousands and maybe hundreds of thousands of different factors that at best would be integrated into one single model.
Okay, is there a possibility to do that at best, integrating everything into one single model, or is that a utopian idea?
I myself am not a statistician and not a developer of statistical methods, or as we talk nowadays about artificial intelligence approaches, machine learning or deep learning approaches. So things which are able to handle large data, because we are talking about the second part of our title of today's talk, big data. Somehow we have a big data problem here. And to integrate that is not just putting things in one row and saying all of this belongs together, but you have to connect them. Are there additive or super additive effects, for example? How do they influence each other? Are they dependent on each other or not? And I think that makes the complexity even worse. And so the answer to your very concrete question, is it possible or not? I very much hope so in the future, sometime in the future. But I think we always have to live with some level of uncertainty. Okay.
Which brings us back to solving the problem of degeneracy, right? If I understand it correctly. Okay. Well, at this point, I don't have any more questions. I don't know if there's anything that you feel is left unsaid, or you want to add anything else?
I think what is quite interesting in this endeavor is our idea that we have been starting to talk about this individualization process. Maybe some of our followers here or people listening to this discussion have been confronted with the idea of a digital twin. That has been in the news, and it's a quite interesting idea. The way you call it might be different ways to find the right term, but the idea that we could be able to create a digital version, whatever that means, not necessarily the digital Lisa, but maybe a digital part of Lisa that contains the most relevant information to manipulate in this virtual setting something to better understand how, in our case, the brain might work. Again, to, for example, better create therapeutic strategies. That, I think, would be interesting. On this side of the digital twin idea, that could be something really interesting, because it can help to optimize things before you go really into the subject, into the patient, when we talk about medical problems here. So this idea of a digital twin, just to put this term here in our interview, is something probably quite interesting. And well, let's see how that goes in the next couple of years.
It does sound extremely interesting, and it sounds kind of very futuristic, or could be the title of a movie.
Indeed.
Yeah. Okay, well, we will definitely stay tuned with regards to this. And yeah, happy about this interview that we just did. So thank you so much, Svenja. It was really interesting.
Thank you. It was fun.
Yeah. So yeah, it was a pleasure to talk to you, and I wish you personally a very good afternoon. And
you too.
We will see each other soon. And I just want to announce that the next LinkedIn Live interview will take place already next week on September 21 at 12 o'clock Central European Time. And it will feature Victor Gierser, who is the director of the Institut de Neuroscience du Système here at Aix-Marseille University. in France, and he will be discussing how he and his team are developing a computational tool that helps to locate the areas in patients' brains where epilepsy seizures emerge. So we hope to see you there, and thank you very much for joining me, and I wish you a great afternoon. Bye-bye.